Hello and welcome back to AP Physics. What we're going to be talking about today is displacement versus time graphs as well as average and instantaneous velocity. To start out with, let's say we had a collection of marbles and the size, we knew the size in the container, the size of the marbles in the container was somewhere between 100 and 500 grams. And we know that the average mass of the container is 300 grams. And I asked you how many marbles in that container would have a mass of exactly 300 grams. Well, the answer is, of course, you wouldn't know. Just because you know the average doesn't necessarily mean that you know what's inside of it. It could be an average of 100 and 500 gram marbles, or they could all be 300 gram marbles. We simply don't know. So the key point here is that when we talk about the average, it leaves out a lot of information, although it is still a useful tool. So let's say we've got a friend here, and he runs 10 meters to get to a wall, and it takes him 2 seconds to do this, and we want to figure out what the average velocity is. Well, the average velocity is displacement over time, which is delta x over t. So 10 meters divided by 2 seconds gives us 5 meters per second. And the question is, why would that be the average velocity? Well, the thing is, the velocity probably isn't constant the whole time. Maybe they start out at from rest, and they speed up and they slow down at the end. And typically, you'd want to slow down at the wall. You wouldn't want to go crashing into the wall at 5 meters per second. So that is just the average velocity, displacement over time. It's not. We don't necessarily know what happened in the middle of that. So we've already looked at average velocity. If we want to talk about how fast something is going at a specific moment in time, we would need to talk about the instantaneous velocity. And the instantaneous velocity, since it can have a different velocity at different times, we have different velocities that we're going to talk about. So this would be your initial instantaneous velocity, v1. v2 would be your final instantaneous velocity, how fast you were going at the end. There's other ways that we could talk about how fast we were going at a specific moment in time. Remember, we looked at, you could have v sub naught could represent the initial time, or we might use vi for the initial time. But we're in this class, we're going to stick with v1 and v2. Although the equation sheet does use v naught and v or vx, and etc. So which does your speedometer tell you? If you're driving along and your speedometer reads, would that be your instantaneous speed or your average speed? Well, your speedometer tells you how fast you're going at a very specific moment in time, and it's constantly changing as you speed up and slow down. So your speedometer reads your instantaneous velocity. So if we wanted to just talk about what happens in between the beginning and the end, okay, we need to use some other tools to talk about that, either graphs or pictures. One type of picture we can use to describe motion, I call a picture graph. We can have an object moving. Oops. They're not going to move. There we go. And we can flash a strobe light. And each time the strobe light flashes at a constant time interval, it leaves a shadow on the wall. And these shadows tell us what's happening in between the beginning and the end, more than just the average. So the key thing is that they're taken at a constant time interval. So if I were to look at my runner again, and I wanted to figure out the average velocity, and I know that the time interval is a half a second. So between 0 and 1 meter, that took a half a second. So 1 meter divided by half a second is 2 meters per second. And they would go have another 2 meters per second here, and they'd be traveling at 2 meters per second here and 2 meters per second here. We would see that their average velocity isn't changing. So their velocity is constant. One way to determine if something has a constant velocity is simply to look at the pictures and see if they're evenly spaced. In this case, the pictures are evenly spaced and the velocity would be constant. So something to keep a mental note of. If something is moving at a constant velocity, then their average velocity is just whatever speed that they were traveling at the whole time. So their instantaneous velocity was the same as their average velocity in that case, if they're traveling at a constant speed. Don't ask me why that picture is there. They were traveling at a constant velocity, though. So here I've got two pictures. One where the pictures are closer together, and below the pictures are further apart. What do you think the fact that the pictures being further apart would mean if these were taken at the same time frame, the same half a second flash interval? Well, that would mean that the person below was traveling at a faster speed. In the same amount of time, they are traveling at a greater speed. The same amount of time, they're traveling a greater distance. What would be happening to the speed of the person here? So here the spacing is closer, and then it gradually opens up. So the person is getting faster, so their instantaneous speed is increasing. And here, the person has their instantaneous speed decreasing as they're getting slower and slower. Another way we can use, instead of using pictures, we can use graphs to describe motion, and these are a little more probably what we're going to do on a regular basis here. We won't use those picture graphs very often. So if we were to take the motion of an object and we were to graph it, so here I've got a little car that's rolling along, and it's at the 10, 20, 30, 40, 50 meter mark, and we were to graph that. So my dots are a little bit off. So here we've got it to motion graphing, and I connect the dots. I'm going to get a straight line. Okay? One thing that's important is if we look at this motion depicted constant speed motion. The spacing was even. When we look at a displacement versus time graph, so again, displacement versus time graph, that's what we've got. A straight displacement versus time graph line indicates that we're moving at a constant speed. Okay? So now if I want to figure out the average velocity after 100 seconds, I can use the graph, and this would be something not too uncommon to do. What I would say is, all right, after 100 seconds, how far did it go? It traveled 60 meters. Okay? And then how long did it take it? Well, we said 100 seconds. Okay? So 60 meters divided by 100 seconds gives us 0.6 meters per second. So that's its average velocity. One thing we said, though, was if it's moving at a constant speed, then its average velocity is the same as its instantaneous velocity. So its speed along the whole line is equal to 0.6 meters per second. Now, I want you to think about what we just calculated. We basically calculated the rise, which was 60 meters, and we divided by the run, which was 100 seconds. So when we take the rise divided by the run, we calculate the slope of the line. So that's something you need to know. The slope of a displacement versus time graph is the average velocity of the object. The slope of a displacement versus time graph is the average velocity of that object between those time frames. So here, if I were to have a different object, there's the dog barking, must be somebody outside, and I had an object that was moving twice as fast, what would look different about its graph if it was moving twice as fast? Well, instead of being here at 10 seconds, it would be up here. It would travel twice as far. And then here, it would travel twice as far. Okay? And what you'd end up with is a line that had twice the slope. Again, the average velocity is the slope of the line. So if something's traveling faster, it's going to have a greater slope. What would the slope indicate here? Well, the slope of the line, since it's flat, is 0, which would mean that it's not moving. And that's exactly what it's doing. It started at the 40 meter mark, and it continued to stay at the 40 meter mark. So its position isn't changing. As opposed to here we've got an object that all of a sudden at 20 seconds teleports from 0 to 100 meters. So this is impossible. We would get an infinite or undefined slope of this line, and that just isn't going to happen. What would be different about this slope here? Well, it's pointed down, which means that the slope is going to be negative. And since the slope is negative, that means the velocity is negative. And remember what we said the negative velocity means, that it's moving backwards. It's moving in the negative direction, which in this case is down this way. So it would be moving to the left if we had our standard coordinates. So here we've got a graph of two cars, and so what's interesting is what does it mean that this car has started, the blue car started at the 30 meter mark, and this car started at the 0 meter mark? Well, it means that the blue car has started ahead. Okay, which car is going to be moving faster, the blue or the red? The red is, because it's got a steeper slope. What's going to happen when these lines intersect? Well, that means that they're going to be even with each other, and then the red car is going to pull ahead. So that's what that graph depicted right there. Now, in the real world, we can't get like these super sharp turns. We have to get these curved turns. And what's happening here is when an object is changing slope, it's changing velocity, it's changing speed, it's accelerating. So as it's changing velocity, that takes time. An object just can't come from moving, because this is moving forward, and it can't just come to an immediate stop. Which is what this would mean. It takes time. So rather than having this distinct sharp turn, we have a gradual turn. What would this mean? Okay, what's happening to the slope of the line? What's happening to the curve of the line? Well, is the slope of the line is starting out pretty flat, and then it's starting to rise and get steeper and steeper and steeper. So since the slope of the curve is increasing, okay, what do we say the slope of the line was? The average velocity. So since the slope is increasing, the average velocity is increasing as well. Okay, and we can check that just by looking at in the first 10 seconds it moved hardly at all. Okay, and then in the last 10 seconds it moved quite a bit. So what would so basically an object with a displacement versus time graph, if the line is getting steeper, it means the object is speeding up. So here we have kind of the opposite graph. We've got a line that's flattening out. Okay? So here the line is starting out pretty steep, okay? And it's getting flatter and flatter until it's perfectly flat. So here it was moving, and here it comes to a stop. So it's slowing down. So as the line gets flatter and flatter, that means of a displacement versus time graph, that means that the object is slowing down. And if I were to look at the average velocity of the different points, okay, so here if I want to calculate the average velocity between 0 and 10 seconds, okay, and then here I guess somewhere between, this is supposed to be 10 and 20, but it moved a little bit, and between 50 and 80. If I look at the average velocity, it's slowing down. It's slowing down. Now, if I wanted to figure out, now, are these I think we've already said, these are the average velocities. Let's say I wanted to know the velocity at a very specific point, because these were figuring out the average velocity over these regions. Okay? If I wanted to figure out the average velocity at a very, very specific point, I would need to know the slope at that very point. So I would take my little rise over run apparatus here, and I would shrink it until it got smaller and smaller and smaller. And eventually, if we want to figure out the slope of a point, we know hopefully from calculus that that is the tangent. So the tangent of a displacement versus time graph is the instantaneous velocity at that moment. It's the instantaneous velocity at that moment. And you can literally just wiggle up a ruler and figure out the tangent and then calculate the slope of that line. If we look at the tangents of this line, those tangents are getting flatter and flatter, which would tell us that the instantaneous velocity is getting smaller and smaller. It's slowing down. So if I wanted to figure out the instantaneous velocity at 30 seconds, I would line up my ruler or whatever, and I would figure out a tangent line. And then I would calculate the slope of that line. Okay, so a little bit of review here. So what's this object doing? Moving forwards, backwards, speeding up, slowing down, or moving at a constant speed? Well, it's moving forward because the line is going pointed up. Okay, it's got a positive velocity, it's got a positive slope. Okay, it's moving forward. Since it's straight, that tells us that it's moving at a constant velocity. And since it's moving forward, the velocity is positive. So it's moving forward, it's positive. Okay, so here we've got a line now, it's pointed down. Okay, the fact that the line is pointed down tells us that it's moving backwards. Okay. The fact that it's straight tells us that it's moving at a constant speed. And the fact that the line is pointed down, its slope would be negative. It tells us that the velocity is negative. Here, this object, it's neither pointed up nor down, so it's not moving forwards or backwards. So that's a trick question. Okay, and it's not moving at a constant velocity. So, since it's not moving, the velocity would be 0. Here, we've got an object. Now, it's curved, so its speed is changing. The first question, though, is it moving forwards or backwards? Since it's moving upwards, okay, it's moving forwards. Okay. What's happening to its speed? Well, the line is getting steeper. Its tangent line is getting steeper, so its velocity is increasing. So it's speeding up. Okay. And the velocity in this case, since it's moving forwards, is positive. Here we've got an object. Which way is it moving, forwards or backwards? Well, the line is still moving up in the positive direction. Its tangent line slopes are still going to be positive, so it's moving forwards. However, since the line is getting flatter, that tells us that it's slowing down. Okay, and the fact that the velocity would be, see if you can check yourself, is it be positive, negative, or 0? The velocity, since it's moving forwards, is going to be positive. Here, we've got it. We've got a line. Now, this line looks a little bit different than the last one for a couple of reasons. One is, as time travels, the line is going down. So that tells us that it's moving backwards. The fact that the line is getting flatter tells us that it's slowing down. Okay? And the velocity, since we're moving backwards, the velocity is negative. Okay? Here we've got an object. The line is moving downwards as time passes, so we're moving backwards. Okay? The fact that it is getting steeper, okay, starts out flatter and then gets steeper, tells us that it's speeding up. Okay? And the fact that it's moving backwards tells us that the velocity is negative.